Good morning again. Today we're gonna start chapter one. Chapter one will talk a little bit about mathematical modeling and numerical methods using MATLAB. Uh, there's not gonna be any examples for now. We're not gonna do any MATLAB examples for chapter one. This is just an introduction to talk about why are we using MATLAB and why do we use numerical methods analysis to analyze engineering problems. We talked about it last time that most of our engineering problems are actually described in equations, differential equations, or and those differential equations can be actually converted to ordinary equations, and then we can solve these using the numerical methods with MATLAB and other software to actually analyze the problems. So I want to actually let me share my screen here and start with the first chapter. It is already uploaded on your on Canvas, so you can definitely, all the lectures are already uploaded there, so you can always access those and go through them before you start watching this these presentations. So chapter one, it is mathematical modeling, numerical methods, and problem solving. So we'll start by what are the objectives for this chapter. First is to learn how the mathematical models can be formulated on the basis of scientific principles. And I mean, those scientific principles could be laws, that principle, like for example, conservation of energy, conservation of momentum, or conservation of mass, or Newton's second law, whatever it is that describe that physical problem or physical engineering problem that we usually, that's how we describe it, through the principles. And those equations or these principles, we want to actually solve this principle by using numerical method. So understanding how numerical method also afford a means, a generalized solution in a manner that can be implemented on a digital computer. Understanding also the different types of conservation laws that lie beneath the models, and we'll just talk about it. Conservation of mass would be one of them. And for those of you who took thermodynamics and fluid mechanics, you are familiar with those laws that we really apply. Conservation mass is one of them, conservation energy, and also linear momentum, angular momentum. All these laws and all these principles will actually describe for us our engineering problem. And based on those principles, we develop the differential equations, and these differential equations can either be solved analytically with a regular solution that we usually do, but bear in mind there's some problems you can't really solve them by hand, because you're going to end up with non-linear differential equation that has no solution except by using this type of numerical solution to do this. And we talk about this more as we move forward with this course. And this is where I wanted to focus more, not so much about the principle of the MATLAB, because you guys took, most of you took Comp 1, and Comp 1 teaches you the basic of MATLAB as a software. This course will focus more on using this software and applying the software in numerical analysis, and how and analyzing engineering problems if it is, again, linear or non-linear differential equations for this particular engineering problem. Okay, we'll talk about more about also the types of numerical methods that we're going to also cover in this course. So a simple mathematical model, just move this one here. A simple mathematical model can be broadly defined as a formulation or equation. We talked about it. It could be like if you're pulling on a spring, if you are actually throwing a ball, a projectile, a fluid mechanics problem, an airplane, a car moving, all these problems can be converted into equations, and these equations will represent that problem. And within this equation, you are going to have a couple of variables. You're going to have a dependent variable, and you're going to have an independent variable, and also parameters and forcing function. And this is true for all problems, all engineering problems. So the idea is that by defining these variables, and you can always start by defining the dimensional variables, and also you can have it as non-dimensional variable. And this is something for those of you who took fluid mechanics. We cover the pi theorem and how you move from a variable dependent dimensional independent and dependent dimensional variables to a dimensionless variables. But it doesn't really matter. You're always going to have a dependent variable, whether it is dimensional or dimensionless, and you're always going to have also a dependent variable. And this is how we present and how we define our engineering problem. And I'm going to give you an example in a minute. What do we mean by these? But just know that there's always independent variables. There's also parameters in this equation, and there's also forcing functions. So what is the dependent variable? Dependent variable is a characteristic that usually reflects the behavior of the state of this system. So that variable is going to be dependent on other variables, and independent variables are dimensions such as time, space, along with system behaviors. And it also depends on the equation itself. So that independent variable is actually will affect the behavior of that dependent variable. And you can have multiple independent variables for a one dependent variable. And parameters usually are constants, reflective of the system properties or for composition. And forcing function is external influences acting upon the system. So give you an example here for a model function example is a bungee jumper in mid-flight. And if you're talking about the velocity as a function of time, you will come up with this equation. Now, in the next slide, I'll show you the differential equation for this and how we came out about solution of this equation. This is an exact solution for this problem. So v of t, which is the velocity of this jumper, is equal square root of gm over cd, hyperbolic tangent of square root of g cd over m times t. So if you look at this equation, you're gonna have a gravitational acceleration in it. There is a mass, there is also a drag coefficient, and there's also the time. So if you look and we try to search what is the independent and what is the dependent variable, so definitely the velocity is the dependent variable because it depends on all of this, the dependent factors, which are the dependent variable, independent variable, which is the time in this case. And also it depends on the parameters, which is the mass and the drag coefficient. So it depends on the shape of this, or aerodynamic shape of the man or the jumper, and also the mass. I mean, how much weight and how much his mass. So that we call these parameters, And sometimes they can be constant, but they have units. They have, and actually depends on the geometry and depends on the physical physics of that object. In this case, the mass depends on the physics of the jumper, and the also drag coefficient also depends on the physics of the jumper as well. Now, the forcing function is usually the gravitational acceleration, which is, again, usually it doesn't change that much, but definitely changes with altitude. But sometimes you can consider it constant, but it does have also a unit. So if you were to plot this equation, and you look at the graphical solution for this, you will see that you can plot this velocity versus time, and time from 0 to 12 seconds, and you can see the terminal velocity, and you see how it is asymptote at this certain velocity, probably around 50 plus a meter per second, as it goes with time. And that really depends, again, on the drag. It depends on the mass, like I mentioned earlier, not just on time. But this particular plot, it just shows how the velocity is varying with respect to time. And this is a true solution. Unfortunately, we have a lot of problems that we really cannot have an exact solution. Now, for those problems that we have an exact solution, so we're fortunate enough to plot this and to solve it. So you can give me the time, I plot it, I can use Excel, I can use any other problem, I can use my calculator and get a velocity distribution or value at certain time. However, in some cases, we don't have this equation that reflect the solution for the problem, or we don't have the exact solution. So what do? We use numerical methods. We use our computer to do the do the work for us, and we'll talk about how we can do that using, for example, MATLAB or other programs. So if we go back to the problem itself, so the same equation which we just showed in the previous slide, that v as a function of t, if you really want to apply the law of physics, and in this case you can sum the forces maybe, and maybe Newton's second law, and say, well, the force is equal mass times acceleration, or you can say that the external force is equal to the change of linear momentum. So that could be one of the principle that we use. So I'm not going to focus so much in this class about teaching you how to use these laws, because when you took dynamics, you probably know you've covered the energy equations, you covered Newton's second law, so you are familiar with that. And we take fluid dynamics, you get the same, thermodynamics, heat transfer, all these classes, they teach you how to use those principles and how you develop these differential equations. So I'm gonna take that differential equation and I'm just gonna try to solve it using numerical analysis and using MATLAB. And that's what we're gonna be doing in class. We're gonna try to pick different types of problem, mechanical engineering problem, electrical problems, all types of problem, meaning fluids, and we're gonna do also solid mechanics problem, we're gonna do electric circuits problem, and all these we are going to come up with an equation, or most of the time it's given to us because we really don't want to have to waste so much time in the physics of the problem. We want to actually learn how to solve these equations. So this is the differential equation. dv dt is equal to g minus cd over m v squared. So if you look at this, now if we were to separate the variable and solve this, we're going to come up with the previous equation, we just saw, and that will give us an exact solution. So in this type of problem, it's really straightforward. We can just do the exact solution. But what we want to do, even though we have the exact solution, we want to see if we were to solve this numerically. How we're going to go about solving this? So this is what we do here. We're going to estimate dv dt, which is the derivative of the velocity with respect to time, is almost equal delta v over delta t. And delta v over delta t is equal v at time t I plus 1 minus v at time ti, right? So I'm taking a small portion. I'm taking, for example, from time 0 second or 1 second to time 2 seconds. It depends on that step that I'm making with time, and I'm measuring the velocity with respect the change of that velocity with respect to time. So if you look at that slope, look at the graph here, and you'll see that this graph is, let me see if I can write here. Okay, so you'll see that between this point here and this point here, I'm taking a step, which is ti here, and ti plus 1. And if you look at the slope, this is the slope. This is what I'm talking about. That straight line is the slope. So if you look at the curve represent the real change of the velocity with respect to time, and the asymptote, or that slope, represent the approximate value. That's why we have this is almost equal to delta v over delta t. So what we're gonna do, I'm gonna break this into small steps of a time. So I'm, instead of going from t equals 0 to t equal 12 seconds at one time, I'm gonna break it maybe into 12 steps. Maybe I'll break it into 120 steps. And the smaller the steps, the better is the smaller the steps is, the better the results that we're gonna get. And this is how numeric solutions and numerical method works. And for those of you who took finite element method, which is, we're gonna cover part of the class, we're gonna do our project based on the finite element method. Even if you don't take it, I'm gonna accept. I'm not interested in teaching you the finite element method. I'm gonna probably cover a small section of that just to show you that MATLAB can definitely be used in finding a numerical solution, and which is a finite element solution. But this is exactly how this works. We're going to divide this domain of time into small segments, and we are going to plot these slopes and add them as they go. So if you look at the Euler method, there's multiple types of methods that can use numerical solution. One of them, and it's pretty much very known method, is Euler's method. Now these, we're gonna revisit this later on. This is just an introduction. We are gonna spend some time in using Euler method, and we're gonna spend some time coding Euler method using MATLAB. But this is the concept of Euler method. As you're gonna say, if you look at this differential equation, dv dt equals g minus cd over mv squared, and if you represent dv dt as v at ti plus 1 minus v at ti divided by ti plus 1 minus ti, remember this is the approximate solution, is equal to, still the right hand side is the same. You can rewrite this by this is what we're trying to find, that value v at time I plus 1 as a function of vti, which is the original. So this is a new, this is all, and this is the slope times the step. Okay, the step means that the delta t, that's again, the smaller the step, the better we're going to get representation of the plot. So mu will be equal old plus slope times step. So if you we plot to this one, and if you look at our steps that we take a 2 seconds intervals. And so from 0 time equals 0 to time equal 2 seconds, you'll see that we have a straight line, as you can see here, and then another straight line, and another straight line, another straight line. So what we did, we broke this into steps and intervals, and that, if you look at the shape of the plot in black, is not really as accurate as the exact solution. However, because probably we took the steps as 2 seconds intervals. If you take the step as 1 second, you're probably gonna get better representation. You're gonna get closer to the exact solution. And if you take it as 0.5 second, maybe you get better and better. So the more steps or smaller the intervals, the better representation for the solution, and you are going to get closer to the exact solution. And this is how this will work, numerical results. And that's exactly what we do with the finite element method. And if you look at SolidWorks simulations, if you look at ANSYS workbench that you guys definitely know or been exposed to, they all work in the same concept because they're all numerical solutions, and that's what we do. We divide the domain into small, very small intervals, and we start solving this. And if you look at this equation here, the previous equation, this is a linear equation, as you can see, and it is what we did here, we moved from a differential equation to a regular general equation, and we solve this in a small interval. And that's exactly how we use numerical solution. Okay, so we convert differential equations, and even if in this case, these are linear differential equations, but again, in some cases, you can have non-linear differential equations, and you can still do the same thing. You divide this big domain into small intervals, and you do your analysis based on the step that you take. Okay, so Euler method could be one of the methods that we use. There's other methods that we're gonna also cover, and there's also some functions in MATLAB that does that does that for us pretty easy, and we'll go over that. But I will talk about how these functions being formatted into MATLAB, and why one function is more accurate than other function. So going back to the basis of numerical methods, so you look at the model, sorry, there is always conservations of laws, and if you look in every single engineering problem, these laws, one of these laws, it has to be involved. So one of them is the conservation of mass, and one of them conservation of momentum, conservation of charge, and conservation of energy. So if you were to solve a fluid mechanics problem, or heat transfer problem, or thermodynamics problem, or dynamics, or even you want to solve solid mechanics problem, all these involve one of these laws, or sometimes you're going to involve three. Like for example, in a fluid mechanics, you're going to involve conservation of mass, conservation of momentum, and also the conservation of energy. So these are the major principle that we always use. So let's summarize of some of the numerical methods. So we are going to cover all these sections. First is the roots and optimization, and this is something we're going to talk about in one of these chapters, one of these lectures. We're going to also do linear algebraic equations, solving multiple equations with multiple unknowns, and find solutions for that. Curve fitting will be one of them. Interpolation will be another one also. And then we move to the integration and differentiations, and we'll see how we can solve an integral or differentiate an equation using MATLAB. And you see how easy it is to do this, no matter how complicated is the equation. So Then also using, again, solving differential equations, and we're going to talk about how we can solve differential equations. We're going to use MATLAB, and we're going to introduce Simulink part of MATLAB to solve these types of equation. All right, so I guess that's it for this chapter. Just going back to how we're going to plan to do this course and how effective we are going to do. Again, for this chapter, there's nothing that it's just an introduction, what we're going to be doing and how we're going to implement this MATLAB software in solving numerical methods. The next chapter, which is going to be a review for MATLAB functions. So what I suggest for you, because I don't know when or most of you took Comp 1, if you are still rusty with this, or people tend to forget things, especially coding programs and remembering functions and things. So it'd be wise to go and if you have a MATLAB book, or you can review, or you can browse the internet and do this. You can also look into this to your books. You can even look at my lecture for next time and look at all these functions, review those functions, open MATLAB and try to practice using again a script or functions or workspace. So you do that. Try to again remember some of the functions. I am gonna do reviews. I would believe probably for the next 4 or 5 lectures. We're gonna do a lot of reviews dealing with again functions, scripts. We're gonna talk about again dealing with matrices and others before we start moving to the numerical analysis and what we just covered today. So definitely I will do a review for this, but also it is your responsibility, because this is not an introduction a class to MATLAB. You guys should be familiar with MATLAB. I taught MATLAB last summer, Comp 1 and Comp 2, so I expect you guys to know how to write script, how to plot, how to do a lot of functions, and how to navigate with this. I will be doing, again, examples, so this way also refresh your memories on a couple of things, couple of functions and how to do plots, how to solve matrices and others. So please go ahead and read the lectures for next time. And like I said, open MATLAB and try to work a couple of problems that are in the lectures, and that's exactly what I'm going to do next time. There's a couple of examples within that lectures. We're going to open MATLAB and try to solve it ourselves using the software. Okay, so I guess that's it for this lecture, and we'll see you next lecture. Let me stop here sharing the screen, and all right, guys, we'll see you in the next lecture. Thanks, bye.